In this statistics video, we will be discussing binomial distributions. Please feel free to press pause and read through today's objectives. All right, first of all, let's talk about what a binomial means. Okay, a binomial experiment in statistics means an experiment that has a fixed number of trials where each trial is independent of the others. And there are only two possible outcomes, which is the reason they call it a binomial, right? Bi meaning two. Okay, so you are either going to have a success or a failure. The probability of success must be the same for each trial. And then the random variable x will just count the number of successful trials. So again, these are going to be probabilities. So make sure that they are between 0 and 1. All right, notation for these, which will be helpful for all of us. Little n represents the number of trials. Lowercase p represents the probability of a success in a single trial. Lowercase q represents the probability for a failure in a single trial. And you find that just by taking 1 and subtracting the probability of a success. And then the x just stands for the count of the number of successes in the trial. All right, so example number 1 is just identifying and understanding them. Okay, so specify the values p, n, and q, and then list the values of the random variable x. And if you can't do that because it's not a binomial experiment, then explain why. All right, so here's the first one. A certain surgical procedure has an 85% chance of success. Okay, a doctor performs the procedure on 8 patients. The random variable represents the number of successful surgeries. All right, so first of all, this definitely is going to be a binomial because we have an 85% chance of success. So right there is my p. So I know my p is 0.85. And if we have an 85% chance of success, then our q would be 0.15, right? We'd have a 15% chance of failure. All right, the doctor performs 8 procedures, so n equals 8. And then the possible values of that, so x could be 0, he has no successes. One of those 8 is successful, 2, 3, 4, 5, 6, 7, or all 8 are successful. So there are the number of successes. All right, next example. A jar contains 5 red marbles, 9 blue marbles, and 6 green marbles. You randomly select 3 marbles from the jar without replacement. The random variable represents the number of red marbles. Okay, so we could easily find the probability of us getting a red marble, which I guess would be considered our success, right? So that number would be our success, which would be boop, 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 boop. How many marbles are there? There's 5 red marbles out of the total 20 marbles in the bag. So 1 out of 4, or 0.25. So this would be 0.25. So not getting a red marble would be 0.75, right? 1 minus a quarter would be 3/4. But notice that it says without replacement. So that means that the first time we pull a marble out, these would be our p and q, but when we go to the next pull, we're missing a marble, so we wouldn't have 20 marbles. So this automatically know is not binomial because the probabilities will change as we go from pull to pull of the red marbles. So this is definitely not a binomial. All right, there is a formula that you can use to find the exact probability of a success for any trials as long as you know the p and the q. And that is just take n, choose x. Okay, so you're going to take your n, choose combinations of x, so the number of successes, multiply that by p to the x power, and then multiply it. So p raised to the number of successes, and then your failures raised to the number of failures. I know it looks very confusing, but once we get started, you will find that it's not too difficult a formula to work with. But definitely have your calculator on standby because this can be found, most scientific calculators have that as a preset in the calculator itself. So make sure you utilize that when you're doing these problems. All right, so let's say that we have a rotator cuff surgery has a 90% chance of success. The surgery is performed on 3 patients. Find the probability of the surgery being successful on exactly 2 patients. All right, so let's list everything out. Okay, we have 3 surgeries, so our N is 3. The probability of a success is 0.9, and our probability of a failure is 0.1. And we want to find when X is exactly 2. So we have 2 successes. All right, so we are going to find P of 2, and we are going to use that formula. So we are going to start with 3 surgeries. We're going to find combinations of 2. So we have to find out how many different ways 2 of those surgeries could be successful. And then we're going to multiply that by 0.90 raised to the 2nd power because I want 2 successes. And then my 0.10, which is my failures, there will be 1 failure. Obviously, if we have 2 successes out of 3, then there would be 1 failure. All right, so that 3 choose 2 turns out to be 3. So then I would just take the rest of this and just plug it in my calculator. So I do 3 times that times that. And again, first power is just, obviously the number. All right, multiply all that, and I get 0.243. So you have a 24.3% chance of having exactly 2 patients that have successful surgeries. So notice the formula isn't too horrible once you get started. You just have to be very careful that this power is the number of successes and this power is the number of failures. So successes, percent of success is your base, power is the number of successes. Failure percentage, failure probability right here, number, and then power would be the number of failures. All right, a survey found that 75% of US adults are experiencing digital device fatigue. I know I am. I don't know about you, but I definitely am. You randomly select 100 adults. What is the probability that exactly 66 are going to be experiencing digital device fatigue? All right, so our N is 100. All right, we need to find our probability of a success. And that is from the survey. That was at 75%, so that's 0.75, which means our failure would be 0.25. And we need to find exactly 66 people. So we want to find the probability that exactly 66 people are experiencing digital fatigue. Okay, so first we have to find out if we have 100 people, how many ways can we choose 66? That is going to be a humongous number, by the way. So just be prepared and don't freak out when it comes up in your calculator, which is another reason why being able to just put all this in your calculator at one point, at one time, is really going to save you a lot of frustration. You're going to multiply that by your successes, so your probability of a success raised to these successes, and then the probability of your failures. So 100 minus 66 would give me 34. All right, so that is good. First of all, this is going to be a humongous number when you put it in there. So when you get it, I think it's going to be 5.807 times 10 to the 26th power. It's going to be a huge number. So again, utilizing your technology here is going to be really important. So put that in, multiply it by 0.75 raised to 66th power times it. Just do it all at once. And usually calculators, if you do it all at once, will not core dump on you. And then, of course, we have to round it, so it's 0.0112. Now, there's always the possibility that your calculator might just say, hey, that's way too big a number for me, you can't do it. But most scientific calculators, if you put all this in at one time, will be able to spit out the answer for you. But if you find that your calculator can't do it, please know that you can find this using any technology you would like. I actually have some examples to show you. So I have Minitab, I have StatCrunch, actually has a binomial calculator where you just put in the information and it spits out the probability, which is kind of great. Graphing calculators like the TI-84 Plus will also have this function, and Excel will also has a function that will find these. So there's lots of different ways that you can use technology to check your work. So just know that when it came test time, I would obviously try to be nice and not give you humongous numbers like that, and just let you you have something a little bit more manageable that your calculator can handle. All right, next example. A survey found that 22% of U.S. adults say that the economy, unemployment, or jobs are the most important problems facing the U.S. today. You randomly select 4 adults and ask them whether the economy, unemployment, and jobs are the most important problems facing them. Okay, find the probability that exactly 2 of them said yes, that at least 2 of them said yes, and fewer than 2 of them said yes. Okay, so this is a kind of multi-step problem, right? We've got lots of things we have to deal with here. So first thing I have to do, let's do number 1. What is the probability that exactly 2 of them? So number 1, probability that exactly 2. All right, so we're going to need to use our formula. So let's go back and find all the things we need to find. All right, so here is my P. So my P is 0.22, which means my Q would be 0.78. My N is 4 people. I'm only asking 4 people. So my N is 4, and the X is going to depend on each problem. So we will just list those as we go. So for problem number 1, we just want to find exactly 2. So we want 4, choose 2, and then we're going to multiply that by our successes. So that's 22%, and we want 2 successes, and failure is 78%, and we want 2 of those as well, because 2 plus 2 is 4. And again, I would put that all in my calculator all at once. You can do it in pieces if you want to, but I just did it all at once, and I got 0.177 when I rounded it. All right, so that's not so horrible. All right, part 2 says find the probability that at least 2 of them. So we need to find the probability that X is at least 2. Now, this will be a little bit more difficult. At least 2. That should be equal to. All right, so that means we have to find the probability of 2, the probability of 3, and the probability of 4. So we have to add all those up. So we have to find the probability of 2, which we already found, plus the probability of 3. So we'd have to do that formula again, and then plus the probability that we would get 4. So we would have to do the formula that we did for part 1 again, but for x equals 3, and then do it again for x equals 4. And this can be tedious. So just know you would do that for each. So the x equals 2, we already have that. We did that previously. Oh, whoops. Helps if I write down 1 correctly. 177 plus. I would redo the formula again. So the same thing, but this time it would be 4, choose 3. And then this would be a 3, and this would be a 1. And then I'd find that. And that turns out to be... Did I not write it down? I don't think I wrote it down. I just think I wrote down what it was. So 4 choose 3 was 4, and then I did the 0.22 raised to the 3rd power, and then times the 0.78 raised to the 1st power, because 3 plus 1 is 4. All right. Plus, then I repeated this, so it would be 4 choose 4, and then I did 0.22 raised to the 4th power, and then the 0.78 raised to the 0 power. Anything to the 0 power is just 1, so I'm not even going to write that down. So I found this decimal, and then I found this decimal, and then I added up the 3, and I got 0.212. Whoops, let me write that up a little bit farther because I need a bit more space to finish this problem. All right. So that gave me 0.212. So I have about a 21% chance that at least 2 people would say that it is. That's not so bad. All right, and then let's go back to the 3rd problem, and the 3rd problem says fewer than 2. Well, the probability that fewer than 2 is just the probability that 0 plus the probability of 1. So again, I would repeat this process. I would find each of those using x equals 0, and then using x equals 1, find each one of those, and then add them up. And again, like I said, this is just tedious and long. But the good news is there are some shortcuts, and we will talk about that in a second. All right, but the probability that fewer than 2 people say it is 0.78, so 78.8%. All right, but as you can see, you're repeatedly using that formula over and over and over again. Now, if you have some very specific success percentages, then we can use the binomial table. And this is one of the great things that'll be on your formula sheet that you can use. So if it has a specific probability of success, in this case we're using 5%. So this one, probability equals 5%. And that happens to be on my binomial probability table that I let my students use. That means my Q is 0.95. Okay, so rather than using the formula, I will be able to look this up. All right, but you have to make sure also that your n is within the values that are on the table that you have. Now, if you look in the back of your textbook, you should have a table that goes for like 20 or 30. Because I just have a short formula sheet, mine only goes up to 8, so that's where I maxed mine out. So n equals 8. And then I want to find the probability that exactly 3 of them, so my x equals 3. So I need to find the probability that exactly 3. Now, obviously, I could still use my formula. So if you would like to use the formula, feel free to do so. You will still get the same answer that I'm about to get. All right, so let me show you the chart, and I will show you how to find it on the chart. So binomial charts look something like this. They're going to have the probability of success up here at the top. So we are looking at this column right here because we had a 5% chance of probability. Then we are going to go down to n equals 8. So go down to the spot where n equals 8. And then you want 3 successes. So you want this row right here where we have exactly 3 successes. So this is my answer, 0.005. And here's the good news. If you use the formula, you'll get exactly the same answer I just did using the chart. The charts are super nice, especially if they ask you to find what's the probability that it was less than 3. Well, that would just be the probability that it was 2 plus the probability that was 1 plus the probability that it was 0. And those are right here. This one is the probability that it's 2. This value is the probability that's exactly 1, and this probability is 0. So I would just write down those 3 percentages and then add them up, those 3 probabilities, and add them up. So these charts are fabulous for those problems where you have like the one we just had where x was greater than 7 or x was whatever. So when so you don't want to repeatedly do the problem, you could just add up these 3 decimals, and then that would give you your answer. So I love using these charts if I can, but the catch is that your probability of success has to be one of the values written at the top of that chart. So make sure that you have discussed using charts with your instructor. All right, so here is a chart. I have clipped out part of it for you. A survey found that 20% of U.S. adults say that the economy, unemployment, and jobs. So same problem, but instead of 22%, it's 20%. So now I can use my chart because it's this column right here. Okay, so we can use that column to help us. Okay, we are again randomly selecting 4 adults. So we are going to use these rows right here where n equals 4. And then we're going to find the same as we found before. So number 1, we need to find the probability that x is exactly 2. So I'm going to choose 4. I'm going to go to row 2, and I'm going to go across that row until I get to this column. So there is my percentage, 0.154. Notice how easy that is. So much easier than using the formula. All right, number 2, we need to find the probability that at least 2 of them, so x is greater than or equal to 2. So that's just going to be, oops, should probably put an equal sign there. So that's going to be the probability that it's equal to 2. I can write. So we want the probability that we get 2 plus the probability that we get 3 plus the probability that we get 4. All right, so probability we get 2, we already looked that one up, that's 0.154. The probability we get 3 is this number right here, 0.026. So plus 0.026. And the probability we get 4 is right here, which is 0.002. So you add all those together, and you get 0.182. Notice how much easier that is. I absolutely love using these charts. All right, number 3. Find the probability that fewer than 2. So x is less than 2. So remember, that is the probability that we have 0 plus the probability that we have 1. So probability that we have 0 is 0.410. And then the probability we have 1 is 0.410 as well. Add those together and you get 0.820. So you have a 82% chance that less than 2 people are going to say that. All right, so notice how easy it is to use these charts. I highly recommend using them. They come in very handy. So, but again, remember your probability of success has to be one of the probabilities that is listed at the top of that chart. All right, can you construct a probability distribution? Absolutely, you can. It's just a little tedious because you're going to have to do that formula over and over and over again. If it turns out to be one of the percentages that's on the chart, then it'll be a little bit simpler because you just copy down those numbers. However, it usually doesn't turn out to be if they're asking you to construct one from scratch. All right, so let's go through one. All right, U.S. adults were asked how often they go online. Results are shown in the figure. Okay, 6 adults. Okay, so that's my N. N equals 6. Who participated in the survey are randomly selected and asked whether they go online several times a day. So we are only looking at this one right here. So our P is 40.48, which of course was not one of the ones that was on the chart. So not good for us. That means we're going to have to do that formula over and over and over again. All right. So they want us to construct the chart. So they want us to construct the chart where X is 0, 1, 2, 3, 4, 5, 6, and then find the probability for each. So we will have to do the formula 7 times. So we'll have to do it for 0 first. So I'm just going to do it for the first one, and then I will show you the rest of the rest of the calculations, just in the interest of time. But so we would start by finding X equals 0. So that is going to be 6, choose 0. And then we're going to do 0.48 raised to the 0 power. And then our failure is 0.52. And we want that to be 6. So we put all that in our calculator. And we should get about 0.020. And then we would repeat the process, right? We'd go X equals 1. And then so on and so forth. And do that repeatedly over and over. So I did that. Here are the formulas for each one filled out. Here's the percentages. And then here is my nice little chart all finished out. And notice when I get to the end, my probabilities added up to 0.999, which is fine. That's very close to 1. And there's going to be some error because I did have to round every single one of these. But it's still very, very close to 1. So that would be totally acceptable. So just notice this would be a little bit tedious and long, but it's just the same. It's the same formula used over and over and over again. All right, another example. 64% of people who survived cancer are ages 65 or older. You randomly select 6 people who have survived cancer and ask them whether they are 65 or over. Construct a probability distribution for the random variable. Okay, this is the same problem. 64%, that is my P. So my P is 0.64. Which means my Q would be 0.36. All right, I am selecting 6 people. So my N equals 6. And then I need to construct, so this time I random variable again. My X could be 0 people, 1 person, 2 person, 3 person, 4 people, 5 people, 6 people. And then you'd have to find the probability for each using the formula before. Again, in the interest of time, I'm not going to make us all do that. But if you would like to take the time to actually do it, please go ahead and press pause and then go ahead and do that. All right, so this is what you should end up with at the end when you've done the formula all 7 times. So those are the probabilities. Notice it does add up to 1. All right, and it should add up to 1 because we have covered all the ages, right? All the possible successes, right? 0 through 6 successes. So we have covered all the successes, so we should have, those probabilities should add up to 100%. All right. If we have a binomial probability distribution like this, can we find the mean, the variance, and the standard deviation of it? And the answer is yes, we can. But the formulas are completely different. The good news is they're very simple, so makes life easy. So if you want to find the mean, all you have to do is take your N and multiply it by your P. That's it, and then you're done. If you want to find the variance, you just take N times P times Q, and that's your variance. And if you want to find the standard deviation, you just take the square root of your variance. So the square root of N times P times Q. So very simple formulas to use, which makes our lives so much easier. So in Pittsburgh, Pennsylvania, about 56% of the days in a year are cloudy. Okay, so that is my P, right? My P is 0.56, which means my Q, which would be a day that it's not cloudy, would be 0.44. All right, find the mean, variance, and standard deviation of the number of cloudy days during the month of June. All right, so June has 30 days, so my N would be 30. All right, so let's find the mean first. So mean, again, as you remember, is just N times P. So that's 30 times 0.56. And that gives us 16.8. Very straightforward. All right, then we need to find the variance, which is N times P times Q. So 30 times the 0.56 times 0.44. And that turns out to be 7.4. And the standard deviation would just be the square root of the variance. So the square root of those three things, so that of that 7.4 value that we found. And that turns out to be about 2.7. Okay, so what does this mean in terms of words? So in the month of June, the mean number of cloudy days is going to be 16.8 days. All right, then it says, and where our standard deviation is going to be about 3 days, right, 2.7. So the majority of days are going to be 17 days plus or minus 3, right? If we round each of those to the nearest day. All right, interpret the results and determine any unusual values. So what is unusual? Remember, unusual is 2 standard deviations away from the mean. So you're going to take that mean and you're going to do plus or minus 2 standard deviations. All right, so if we do the low end, so 16.8 minus the 2 times 2.7, that gives us 11.4. So anything less than 11 cloudy days would be unusual. And then if we do the high end, 16.8 plus the 2 times 2.7, that gives us 22.2. So if we have more than, so 23 days or more of cloudy weather, that would also be unusual. So it gives you the high end unusual and the low end unusual. So make sure you cover both sides. But again, remember, unusual is more than 2 standard deviations. All right, so let's give you a shot. Same problem. I just looked up some different information. And since I grew up in Colorado, I chose Colorado. So please press pause, read through the problem, and then follow the instructions and find what you need to find. All right, welcome back. So let's see how you did. The N is 31 because there are 31 days in March. Some of you may have put 30. Remember, there are 31 days in March. The P is 0.28, is 0.82, that's the 82%, and Q is 0.18. So I found the mean. There's my formula. I plugged in my values. I got a mean of 25.42 days. So on average, there's about 25.4 sunny days every March. Found the variance. Again, that's N times P times Q. Plugged in all that. Multiplied those. That's 4.58. And then the standard deviation is just the square root of that, which is 2.14. So the standard deviation is about 2 days. So 25 days, give or take 2 days, is what we expect the majority of the time. 68%. All right, so if you want to find those values that are unusual, you're just going to take that mean, subtract the 2 standard deviations, which would give you 21.1. So a March with 21 sunny days or less would be unusual. And then the high end would be the mean plus the 2 standard deviations, which gave you 29.6. So a March with 30 sunny days or more would be unusual, right? Where you didn't have any cloudy days at all, right? Or maybe just one day that was cloudy. Anyway, so hope this helped. Binomial distributions, please, again, hope for those P's that are on your chart, because it'll make your life a lot easier not have to use that formula all the time. But feel free to come back next time and we'll talk a little bit more about probability distributions.